good to go if you need to pick up a few things on your own. And so yeah, take a picture is probably the best way. I'm going to talk about each one of these. I will not have time to entertain too many questions, but I will be available all day tomorrow if you want to stop by or send me an email just to ask questions. So, now it's time to pay attention so at least you hear something about the importance of these things. The last thing that I have not put up on the board is the transportation of the gases. And that was one thing that was covered in lab, correct? How is CO2 carried as a bicarbonate ion? Well, I want to go over it anyway, but let's do this first because it's not covered in lab. Right here, we're going back to the picture where we were at the end of the last class. We were dealing with the oxygen levels then, were we not? The PO2 of 101 versus 40. Remember that? Okay. Now, this is the very same picture, except we're dealing with carbon dioxide. Both of these are going on in the same place at exactly the same time. But putting it all on one picture just blows your mind. So once you learn it for oxygen, know that carbon dioxide is happening at the same time. So when that blood is coming in from the heart, it's dirty blood. So it's going to have a PCO2 of 45 to 46 mmHgs. That's dirty. What was the PO2? 40. Okay. So as it passes through this same capillary, this is the same air. The PCO2 in here is 39 to 40. 39 to 40. That's a fact you have to know. So if it's 45 here and 39 here, the CO2 is going to get out of your body during expiration. The cleanest it's going to be in CO2 is the PCO2 of 40. That's just what you have to know. 40 versus 45. 101 versus 40. Okay? So now this blood goes to the same big toe as the oxygen, and the PCO2 is 40 mmHgs. Comes in like this, and if this sphincter is open, that means the tissues have been functioning and CO2 has been made, right? It happens to be the PCO2 is between 45 and 46. What did we say it is in the cell? What's it in the cell? 0. Why?
Very soluble.
Because of its solubility. It gets out right away. Solubility of 20. So here it comes. Here it is 40. Here it's 45. So naturally the CO2 is going to go in. So over here, the PCO2 is 45 to 46. That is up here. Correct? Make sense? Okay. So, if I ask you a question in a test, I'm going to tell you. I want to know such and such. As it enters the tissues, that means over here, or enters the lung, we're talking here. Exits the tissues, exits the lung. I won't ask you other scientific terms, but just those. So someone's going to raise your hand and say, what do you mean by entering the tissues? It means it is clean. low in CO2. Okay, so now I want to say a little bit more about this right here, the respiratory membrane, because this is your exposure to the outside world. You're vulnerable, the respiratory membrane. And the younger you are, the more dynamic your tissues are, the more vulnerable will be that cellular partition. So here it is. This is the capillary filled with blood. PO2, 40. PCO2, 45, 46. This is the inside where the air is, which was 104 and 39 to 40. These cells that make up this sac are either simple squamous or simple cuboidal. The squamous ones are called type 1, and the square ones are type 2. The type 2s are the ones that make that detergent called what? Surfactant. That keeps the seriously pressure down so that they won't collapse. Very important. Running around inside here in great quantity are a number of cells called dust cells, and they're not dust, they're dust cells. They're macrophages. If somebody is rude enough to sneeze in your face, you might want to have these macrophages to gobble up what your neighbor may have given you. Nice to have. Now, between these cells and the simple endothelial cells of the capillary is some wispy connective tissue with elastic fibers made by fibroblasts. Makes this very stretchy. These two lines will have to be the basement membrane, because this is epithelial tissue. Also in here is a little jello and plasma cells to shoot antibodies, mast cells to regulate the fluidity of the jello, and some more macrophages. You want this to be dynamic and movable, expandable and contractible, because you're constantly breathing in and filling them and breathing out and reducing them in size, correct? So healthy, this you need. If it gets too thin, some of the water from the blood can go into this space and you'll have pulmonary edema. If it becomes too thick, like pneumonia, it takes too long for the gases to go across, and you won't get rid of your gases or get gases properly. And then it's possible that you could suffer from a condition called dry lung. Dry lung sounds like it's bad, but it is not. Dry lung means that you have enough special albumin in here so that the water is not going to want to escape into the lung, but actually will be encouraged to go in here. You don't want the water in your blood to slip into this space filled with air, because you drown. That's what happens when people's hearts stop functioning properly. It backs up, and that water goes into their lungs, and they die by They die from drowning from within. It's horrible. You can hear that gurgle, gurgle. Actually hear it with your ears, not a stethoscope. Yeah.
You said if it's too thin going into the lung, it can cause what?
It can make some of the water that should stay in here to slip into here. And that's called pulmonary edema. Okay? So you want this to be healthy. And as I said, young children's lungs are so dynamic and alive. You don't want to expose cells that are constantly mitotically dividing. You don't want to expose it to carcinogens because it sets them up for potential cancer in the future. That's why a 12-year-old kid smoking a cigarette is way far worse than a 42-year-old person because their lungs are not so dynamically dividing. And they're also past that stage of vulnerability. That's why when you go in to get a bunch of x-rays, the first thing they'll ask a female is, are you sure you're not pregnant? Because we don't want to expose those young dynamic cells to potential carcinogens because those cells are so vulnerable. So I always suggest, tell your kids, it's not good to ever smoke, but it's worse to smoke at 12 than it is at even 21. So look at the respiratory membrane's composition. Understand the role of all these cells. And if, for example, if a person, individual alveolar sac is supposed to look a lot like this, like a cluster of grapes. After exposure to carcinogens, tars, and nicotines, and all of these other things, and not just that stuff, but industrial things, pollution, this business can end up being all removed, all destroyed. And so now instead of having each little grape be able to go push on it, you've only got this. And the air becomes trapped in here. That's what happens in emphysema and pulmonary, obstructive pulmonary business. And so in these people, they have to walk around with a constant source of oxygen. Now, I always like to tell this story because it was scary. Years ago when you could smoke wherever, I went to a really nice restaurant. People just, naturally smoke. And in comes this older couple, a woman pushing her husband in a wheelchair, and he has an oxygen tank hooked onto the back of his wheelchair, and they have dinner, and he's all this business, which of course is not one being judgmental or anything, but that was hard to take. However, is right. After dinner was over, he pulls out a pack of cigarettes. And I thought, well, that's his business too. I mean, obviously he wasn't that far away from death. If he wants to smoke till the day he dies, that's his business. However, you don't go striking a match next to an oxygen tank in a public restaurant. And so he started, I went over there. I said, excuse me. I really don't mean to be obnoxious, but please, I don't want to, have an explosion in the restaurant. And I just, to get to that point was just beyond me. So I don't know how many of you guys smoke it, but honestly, it's the worst thing you can do for yourself. Absolutely. And the problem with people who smoke is they think, and I used to smoke, they think that without smoking, they'll never have that sense of satisfaction and well-being again. That's what makes it so bad to give it up. Believe me, give it up, and you will be very happy you did. At least when I was smoking, that was an in thing, you know. They didn't know all the things they know today. Today they know too much, and it's no longer cool. I was driving down the road, going to my house the other day, and 3 or 4 little, I might have mentioned this, 3 or 4 little kids had just gotten off the bus. They must have been like 12 or 13. They struck up a cigarette. They're walking. Yeah, I'm like, oh, so cool. I rolled down my window and said, "You think you're cool? You're an idiot." So, anyway, and they are. Of course, they're young, so, you know, you can excuse that. Of course, I can't imagine them thinking they're going to go in the house and have a mother not smell them, you know, like that. The mom probably smokes too. Anyway, let's go over here now to this picture. So, how do you breathe? We've heard that you have to create a gradient to get the air to want to come in and go into those sacs. And then you have to create a greater gradient in the sac to squeeze it out to put it outside. So, inspiration is the active part. And that means that if you're being told to do so by the medulla oblongata, one of the forming things, this whole thing is called the medullary rhythmicity center, this part in the medulla. This is the medulla, this is the pollen. This is a sliver nucleus called the inspiratory. This is the expiratory. The dominant one is the inspiratory. It's sometimes called dorsal ventral. I don't care which one you use, but I'll probably use medullary rhythmicity just to let you know that it's in the medulla. And these nuclei are hooked to the phrenic nerve that goes to your diaphragm and your rib cage, influencing the inspiratory will be a pair up here called the pneumotaxic and a pair over here called the apneustic. They're sometimes just called the pontine. Well, I'm not going to expect you to remember that this inhibits and this stimulates and all of that. I only want you to know that these two work together to help make sure that the transition between your breath is smooth. You don't recognize people next to you by going, they're not doing that, are they? The reason why they're not doing that is because these two work to make it smooth. Everyone's smoothly breathing in here. What controls how many times is the inspiratory. And the way it does it is this. It starts to send a message around itself, action potential. While it does so, it sends a message to the expiratory saying, don't bother, don't do anything. It sends a message down the phrenic, and that makes the diaphragm go down and the ribs go up. Make sense? That lasts about 2 seconds. And this becomes fatigued. It totally stops sending the message for 3 seconds. And then it starts again. But if it waits, if it holds off for 3 seconds, this is going to have to snap back up, isn't it? Natural recoiling of tissue. The rib muscles have to contract. So that's going to make the pressure in this little alveolar sac, the pressure is this way to push the air out. So that's passive expiration. Then, of course, this starts up again. 2 seconds later, it stops. Now, it just so happens that sometimes when you overindulge in booze, you know, in those frat houses, you know, they're all partying hard, funneling and doing all the stuff they think's cool, along with cigarette. The alcohol goes right here. And so somebody crawls upstairs in one of the rooms, and falls unconscious upstairs. Well, no one's there to notice, and all of a sudden, it stopped, but it didn't start up again. And there you are, cold as can be by the morning. You're dead. Because this stops wanting to turn on. And so had somebody noticed, ooh, I don't think he breathed. Let's, artificial whatever, and put him on an intubator, and he would have been okay. Maybe killed a bunch of brain cells, but that's okay. We got a few spares. Anyway, this is what basically controls how many times you breathe. We know that these are things that can affect it, however. They say your limbic system especially is influential because when you become fearful and afraid, it tends to speed it up, doesn't it? Or nervous. However, one of the bad things about the limbic is if you breathe, and I think I brought that up in the limbic system, that if you breathe too long, I mean, like my niece was a flu, or her husband died 30 years ago and she's still breathing. That's a little long. They know that breathing makes you breathe less. And so it affects all kinds of things, including your immune system. You need to breathe about 12 times a minute to be perfectly in balance. We know that we have some chemoreceptors. These are blood vessels right here called the carotids. You've heard of them before, have you? Because a lot of people's carotids get corroded and they don't think so well because the flow of blood to the brain is limited with oxygen. Well, there are some chemoreceptor cells lining the carotids that pick up on how much oxygen is in your blood. And if it's low, it tends to tell you to breathe more often. It's not very, it's not extremely important. Actually, the number, mark my words, the number one most important factor that affects how often you breathe is what is your oxygen, your carbon dioxide level, the PCO2. A fourth grader would say, well, of course it's oxygen. We need oxygen. No, it's CO2. If CO2 gets off just a little bit, that is what rings the bell that says breathe more often. So, we know if we breathe in too deeply or we expire too long, both of these extremes are picked up by the lining up by this alveolar sac. They pick up on it and they ring the bell in the medulla that says, breathe some more. This is a stretch receptor. This is a deflation reflex, picker upper. The reason why is if you're spending a whole bunch of time going, way too long, or you're going way too long, you're having fewer breaths per minute. You need 12, and you're spending so much time breathing in deeply, you may be 10. So it's not after a point, gas exchange stops being optimal, and you gotta get off it and get onto a new, fresh whiff of air. You understand what I'm saying? Do you? Okay. And then we know, of course, irritants, even, just think of coming out of a house and it's freezing cold. It usually catches your breath. Things like that, acid in the air, Clorox, all of these types of things affect your breathing. And then, of course, your cortex. You can tell yourself to hold your breath. And you can tell yourself to blow out. You can do all kinds of things. Actually, to be a really good singer requires that you have cortex involvement. That's why I say even these dirty rappers, they gotta be smart enough in order to rap. They have to have a cortex. I don't know what part's working, but it's working in order to be able to do that. Okay? So at least read about some of the influences on what allows you to breathe normally. Now, what kinds of questions do you have so far before I go into the transportation of the gas? Yes.
Are the disorders of the lungs influenced?
Oh, well, it doesn't hurt to know about emphysema because it's become so commonplace, but I'm more concerned about not so much the name as the problem. Yeah. I mean, definitely you should know that you don't want your membrane to be too thin or too thick. That type of thing. I think any question that might have something to do with it would be have enough information in there for you to pick up without having to know the name. Somebody else?
You elaborate on chemoreceptors, what's that?
The chemoreceptors, they're just cells that line the carotid, and they pick up on the amount of oxygen being carried in that blood. And if it's too low, it encourages you to breathe more often so that you can get some more oxygen. By the way, hyperventilation is one of those things that you might want to know, because a lot of people, even in this room, have had a hyperventilation experience where you start to breathe rapidly. Well, that can be due to anxiety, it can all kinds of things. But when you do, what happens is you keep spewing out CO2 so much that you're going towards alkalosis. Most kids would say, oh, I think that's acidosis. No, when you spew out carbon dioxide, you're spewing out your ability to make acid, carbonic acid. And so you are really suffering from alkalosis when you are having a hyperventilation response. And that's why they say breathe, they used to say breathe in a bag, because you're taking you're keeping your CO2. You see what, they now don't treat it that way so much EMS wise, but if you're all alone, you can breathe in a bag, and it'll help you get over the event. Okay, so now, real quickly, I'm not going to handle the oxygen nearly as much, but more the CO2. But just know that if this is your alveolar sac here is your capillary. This is one red blood cell, which is about the diameter of your capillary. It doesn't have a nucleus, instead it has a clump of hemoglobin, a molecule, which has iron, heme, as a part of the hemoglobin, you have embedded in it heme. And so that when the oxygen goes across, it has a natural affinity for this iron. It loves it. It's where it wants to go. And when you have more than 2 oxygens attached to the 4, it's said to be oxyhemoglobin. Otherwise, it's deoxyhemoglobin. So, the thing that's interesting though is that these places that want to hook onto oxygen, they also love carbon monoxide. And carbon monoxide is what's produced from poorly functioning heating systems. It's odorless. And so when you start to breathe it in, this goes over here and hooks on instead of the oxygen. And it doesn't want to get off. It just clamps on. It has no reason to get off. So in time, if all of these places that are supposed to have oxygen have carbon monoxide attached to it, guess who's gonna die? And that's what happens to people who, die of carbon monoxide poisoning. Even if you save a person, you find a person who's got the cherry-colored lip, you haven't saved them yet. Because if they're really far advanced, you have to put them in a hyperbaric chamber or something in order to get this to come off. It doesn't want to get off. So you have to supersaturate the oxygen and it forces it off. So anyway, why oxygen wants to go on here has a lot to do with its affinity, the concentration gradient, the acidity, and the temperature. All of these, this environment is just perfect to make oxygen hop on. Well, if you get out, and here is a capillary in your big toe, and here it is, right here, and here is a cell. What's the PO2 here? 20. What is it here? 40. What is it here? This is coming in. 101. Okay, so isn't there a natural gradient? Oxygen will hop off because there is less oxygen. So it gets off and goes into there and cellular respiration. Also, because what makes oxygen want to hop off, most of all, aside from affinity, lack of affinity, and all of this, is what's called the Bohr effect. The Bohr effect says, because it has a low pH, high acidity, low pH, that's what makes the oxygen want to get off more than any other factor. And that is called the Bohr effect. It wants to get off, of course, because of the gradient. It wants to get off also because the temperature is a little warmer here than it is here. But its number one reason is the Bohr effect. So I'm not going to say much about a lot of things, but we cover it a good bit in 318. It's more difficult for you all to appreciate the transportation of CO2 and its importance as a buffer. And that is what I want to attend to right now. So, here is a gigantic capillary in your big toe. This is a big red blood cell, and here is the hemoglobin. Hemoglobin is protein, NH2 carboxyl group. Here is a cell. It underwent cellular respiration, and it gave off CO2. Think of this as all the CO2 in your body. The first thing it will do is go into a capillary, correct? Because this is the correct PCO2s. Now 45 to 46, 40, 45 to 46. So the CO2 comes in. There's going to be three ways in which it's transported. Dissolved, this is bicarbonate. Some people call it carbonic acid, but dissolved 7%. Carbamine or hemoglobin 23%, and 70% for the bicarbonate method. So these are the three ways. Did you learn that in the lab? No. Okay, some did, some did. Okay. So obviously, 7% is going to be carried dissolved in the plasma. That's not going to be enough, is it? You're going to die. Well, the other 23% goes into the red blood cell, and it attaches to the amine group. You've got amines everywhere, don't you? I mean, this is a huge molecule with a bajillion NH2 groups and carboxyl groups. So the carbon dioxide attaches to an NH2 group. It holds it like the kid in the mall. If it's held, it can do no harm. So 23% will be carried in a harmless way this way. And 7 dissolve. But now we still have 70% to take care of. Okay? With me? So here goes some of the CO2 is in here, and present always is the universal solvent, water. And in these red blood cells is going to be this special enzyme called carbonic what? Carbonic anhydrase. Enzymes allow something to happen. What it allows it to happen is become H2CO3. What's that? That's carbonic acid. Is that a weak one or a strong one? Okay, if you don't know the difference between a weak and a strong acid, look it up. This, therefore, is going to dissociate into this and this. What's that?
Bicarbonate.
The bicarbonate. So this is gone, right? So the bicarb, and what's that? Hydrogen ion, that is a terrible free radical. Well, next, the HCO3 is going to shift out like this. And because we're talking bajillions, all of these negative charges exiting, what's going to come in? You learned it in the lab. If you did learn it in the lab, part of it was your fault. Part of it was the teacher's fault. Negative ions, the chloride ion is going to shift in. It's called the chloride shift. Well, do you see a potential problem? Is this not one of the strongest acids you can have? And is it going to dissociate? Can it? No, it won't dissociate because it's strong. It loves to be together, lower the pH, and pickle the cell. So what do you think is going to have to happen before this happens? While this shifts out, this shifts in, what's going to happen to this? Sit around waiting for this to pickle yourself? Yes. Goes up here and is picked up by another NH2 group. That's why we studied the amine and the proteins in the very first class practically. So now this becomes NH3 on this end. So this protein or amino acid is a buffer. So if this is being held up there, you don't have any problem going on here. Well now, if you're smart, you're thinking, why in the world do we have to go through all of this? Why can't we just let it all dissolve in here, get it to the lung, and blow it out? Because while this negatively charged ion is flitting around in your plasma, it's available to pick up hydrogen ions if you're going into acidosis. What would happen if you started to exercise and you started producing a bunch of lactic acid? Don't you have to have something to hold that so it doesn't plummet your pH? If you're supposed to stay at 7.35 to 7.45, if you, in this case, this little bicarb, if you had a bunch of this produced, either from your diet or exercise or whatever, you got to get it off the street. This will say, come on over here, and I'll hold you. And it becomes carbonic acid. If you work towards the other, then it will give it up and go back to this. It's a buffer. It is keeping your plasma from dropping the pH and pickling you. That's why, if you don't understand buffers, please read about them, because you're all going into fields where buffers are going to keep you alive or kill you. One or the other. It's that important. Now, when this blood gets close to your lung, you're going to have to do a switcheroo, correct? You learned that in lab? Did you? Some of you act like you didn't. But if you're getting close to the heart, you're going to have to have, close to the lung, you're going to have this bicarb shift back in and the chloride shift out. This has to come down and become H2CO3, And then the carbonic anhydrase has to do its thing again and turn it back to the carbon dioxide and water that it was to begin with. That's why you see reversible arrows every time you see that reaction. You know, it's amazing. I mean, it's amazing how unexcited people are about things so fundamental to their health. Amazing. Absolutely. So, if you learn this in lab, thank your lab teacher. If not, now you get to learn it. Because this is so important. Think about it. I'm available all day tomorrow. If you need